Hi, I'm Seongju Lee from Hanyang University. I will introduce our work named Legion, Tailoring Group Neural Execution Considering Heterogeneity on Multiple Edge Devices. Nowadays, lots of deep learning applications are used, often with high-performance devices in cloud server for efficiency. Local edge devices also can be used for inference to meet a short deadline or to protect privacy of users. However, as recent deep learning models have increased in complexity, substantial performance degradation can be shown on a single edge device. There are various promising techniques to concurrently utilize multiple devices, and we have focused on model parallelism in this work. Because model parallelism requires layer-wise workload distribution basically, outputs of every layer on each device must be merged, which requires a lot of data communications. To handle this issue, some layers can be fused as a one group to be executed in each device without interlayer communication. It helps to reduce the number of data communications, but it also increases the input size of the layer groups because the given input must cover from the first to last layers in the group. Therefore, it is important to determine the optimal fusing points considering the trade-off. However, substantial cost for searching the optimal fuse layer configuration is a problem. For this, we need to fill costs of all possible fuse layer groups in a matrix named cost matrix. For example, T1, 2 means the cost of fuse group consisting of first and second layers. Here, we can naively think a method named full searching scheme to profile all layer groups to find the best configuration. However, it is much inefficient because it requires substantial amount of compilation and execution time to fill all the elements in the table. Another way is to construct a regression model to predict runtime on each device. It is relatively accurate, but it still requires massive amount of training data and much time for its construction. So our objective is to reduce the search cost for finding the optimal fuse layer configuration by minimizing profiling overhead. To do this, we propose metrics-based lightweight cost prediction and additional fusion named wildcard to tolerate profiling error. The figure shows an overview of our framework, Legion. If the target network is given, preprocessor arranges available devices and extracts layer features including kernel size, padding size, etc. Then predictor estimates overall costs for all possible fuse layer groups with minimal profiling. Lastly, optimizer searches the best configuration based on the profiled results. If the optimal configuration is determined, networks with fuse layers for each device can be compiled. A key solution in our work is cost prediction with minimal profiling to reduce search cost for the optimal configuration. First, Legion splits input data along the height dimension proportional to performance of each device to parallelize multiple devices. For example, relatively high performance device gets larger portion of the input data and slow device takes smaller chunk. Then the computational overhead induced by fusing some layers named alpha can be evaluated as sum of the height of orange and red box in the overlapped input by height of orange box in the original input. To predict overall costs of each fuse layer group, Legion constructs cost matrix based on four matrices. Alpha matrix contains alpha values evaluated after overlapped input size of fuse layer groups on each device are determined. Set run get matrix contains profiled costs of non-fused single layers for sending data, execution, and receiving data in each. Now, suppose we want to evaluate the value T1, 2 in specific device D, which is sum of the three costs. Because input data for each device increase as layers are fused, profiled sending cost from send matrix should be multiplied by overhead ratio from alpha matrix. For the same reason, profiled execution cost of each single layer must be multiplied by corresponding alpha in each, then they can be added. As the size of alpha feature map doesn't affect it by fusing, profiled receiving cost from GAN matrix can be used as it is. In this way, predicted overall costs of all possible fuse layer groups are filled in the cost matrix with the maximum value among the devices. With a complete cost matrix, Legion can search the optimal fuse layer configuration based on dynamic programming by summing all costs of consisting fuse layer groups. However, prediction faults can occur because of trivial variation in profile runtime performance. Therefore, we apply a second solution named wildcard, providing an additional opportunity to fuse two most effective layer groups once more. Then the new candidate configuration can be accepted as an optimal one if it shows less latency. These are our experimental setup to evaluate the performance of our work. VGG and YOLO V2 models are used for inference with TVM, LLVM framework, and ARM-based CPU in devices named Firefly RK3399 and Odroid XE4. First result is the comparison of latency improvement applying layer fusion, adding Firefly or Odroid one by one in each environment. X-axis indicates device configuration in each environment, and Y-axis indicates latency improvement compared to the case when only a single device is used. Also, the cases in which the wildcard was effective were marked as improved with an orange box. We can see that fusing layers reduces latency as the number of devices used increases by doing inference faster up to 2.4, 2.5, and 1.4 in each model with 6 devices. Also, Legion shows only 3.4% performance loss compared to the full searching scheme, and wildcard can further improve its performance in some cases by catching more efficient configuration. Second result is about comparison of compilation and execution time for profiling. Y-axis here means overall profiling time in each method, full searching scheme, and Legion. Legion shows much less profiling time compared to the full searching scheme, 48.7 times faster profiling on average. Now here's our conclusion. Processing capabilities of single-edge device are easily overwhelmed as models are becoming complicated. We can consider layer-wise model parallelism, but cost for searching the optimal configuration is substantial. So we proposed lightweight orchestration framework, Legion, which searches the best configuration with minimal profiling execution. Legion significantly reduces profiling overhead with only small performance loss in both homogeneous and heterogeneous environments. If you have any questions, please let me answer in Q&A session after the presentation. Thank you for listening.